Okay, we're starting with or without students, which means we'll have a short class today. Because all of you are sitting here listening to me on the previous class. You guys are returning. You guys in the back, are you returning or are you new? You're returning. So, you returning or are you brand new? Returning. You've been here before. You've taken my... Yeah, I know I saw you like hours ago. Okay. Which means I can skip everything about bhacker.com and the EMS and everything, right? Okay, perfect. I'll just go over the syllabus. I want to give you this information about this book that you need to go get, actually. It's a required book for this course. And then I'll show you a little bit. I think I'll skip the lecture. We'll have a very short class today because I'm going to have to repeat everything next week. And I don't want to bother having to go through this twice and bore you guys to death to begin with. So we'll make it easy for today. I'm not quite sure what's going on. I think people didn't think I was going to have class today. I think that's what the situation was. So, but you guys did show up, so we're going to have class. Here we go. We are going to talk about data structures. Have you guys ever taken a data structures course before? No?
We had something in C++.
Okay, but not very much for data structures. Excellent, because I'm going to talk about this is geared towards more of an undergraduate data structures course. However, it's at the graduate level, which means I need to make it a little bit challenging for you. But it's really an undergraduate subject, and it goes really well with programming. And you guys are all taking the Java course? I know you three are. You two are. Have you taken the Java course before?
Completed in the spring.
Ah, perfect. You guys in the back are, I saw you guys earlier today. In the morning. So you're taking that Java class too. Perfect. Because I'm going to teach this course with a Java focus. So this course will complement really well with the object-oriented programming course in Java. So if you've got Java experience, way to go. If you're taking the Java course, this one will come right along with it. Because data structures is really a programming concept. You have to apply it to some language. You can't just say data structures, no programming language focus. So I picked Java because I'm teaching Java as well. So it'll complement quite well. So what we're going to do is look at, in this class, go over common data structures that are implemented. It is not required that you use Java, however. If you don't like Java, if you like C++ better, you can take that option. The assignments, and I'll go over that in a few minutes, can be done in any language. You don't have to use Java. But I'll be talking about a lot in terms of how the Java is implemented. Because it's all automated and it's a lot easier in Java. So the topics we're going to cover: in-depth presentation of recursion, collections, iterators, some theories, stacks, queues, lists, linked lists, concepts of structures in terms of how they apply with programming and software engineering. And it's a basic data structures overview course. As I say, it's very much an undergraduate kind of level. So it should be fairly easy for some of you, I think. So we can go through and you can look at the course learning objectives on your own. Here's the book that I keep talking about. It's called Java, I'm going to make sure this is correct, the 3rd edition. Yeah. In fact, I can send this around if you guys want to take a look at it. This is a used copy of it from Amazon. It was about $40-ish. You'll probably find it cheaper. I would prefer that you get the 3rd edition of it. The reason why the book is going to have a lot more reading and a lot more explanation than the lectures will. I'm going to use the slide set that goes with the book for the presentations. And the slide set only shows you a little bit. The book's got a lot better reading in it. And for data structures, it's kind of the type of course where you can't go on Google and look it up. It's the foundational concepts that's a lot better delivered via book. I picked a book that was kind of thin, that used Java. So this book will actually work for both the Java programming course, although it's not an object-oriented focus book. But it shows you a lot about the Java language, the Java data structures that are implemented in Java, which is all automated. So we have collections and lists and things that are packages, libraries, that are built into the Java libraries. So you don't actually have to reinvent the wheel like you do in C++. You heard what I said earlier in the Java class. That's why I like that particular book. It's a really easy read, nice questions. For those of you who get the book, you'll be at an advantage. Because if you notice at the end of each one of the chapters, there's review questions and stuff. I'm going to base the exams off of that. I'm going to base the CSLO essays off of that. All the class activities. The assignments are not in the book, though. The assignments don't come out of that. But when you come to take the final exam, just know right now, those are the questions. So it's twofold. You'll be more successful in the course. You'll learn more about the structures. You'll get the background information you need. And for this type of course, you need a book. I can't teach you without a book. So I don't normally assign books and don't normally teach from the book. But the nature of this particular course, it's very driven by a book kind of thing. So what we're looking at then is designing and using data structures. Excellent, 3rd edition, still out as of 2010. It should be fairly inexpensive. You might be able to find an international version of it. Order it online. Most likely, you could have a 3 or 4 week delivery on it. You can get cheap copies of it. It's all over the place. Everybody uses this book now for data structures. So what have you got? Just like the Java class, actually. There's 4 assignments instead of 5. And there's the final exam, there's a midterm, and then there's a CSLO. And as I mentioned before, I'm going to pull questions out for the CSLO and also for the midterm out of the book. So you'll have the answers in the book. I mean, the questions are at the end of the chapters. The material in the book, if you read it, will give you the answers, essentially. So the midterm exam will be a take-home exercise, just like the Java course. The final exam will be an in-class exercise. The CSLO will also be a take-home exercise. The homeworks, there'll be 4 homework assignments. I actually have the course out. Let me find the course. So, here it is. I do not have the midterm, and I do not have the CSLO essay, but it will be populated within the next couple weeks. But I do have the 4 assignments, if you care to look at them. I also have all of the lectures out and available, and I'll be putting their video recordings of the class sessions in here as well. And just to take a preview of one of the assignments, here's assignment number 1 as an example to kind of show you the difficulty level, give you kind of a preview of what to expect in terms of the level of difficulty. Because that's one of the concerns of most students is, you know, this is going to be a hard class. Am I going to be able to handle the work? I'm brand new to programming. I'm a healthcare person or something. Yeah, you can. It's a lightweight course. It's not a heavy duty. It's not a math class, although a lot of people think data structures and math have a lot of, really it doesn't actually. It's not a math-based course. It's more of a programming language-based course, if anything. So here's an example. And as we go through the course, I'll go through each one of these things. The first assignment will be on linked list. We'll have one on collections, one on stacks, one on queues, and different types of data structures. And it basically gives you an opportunity to implement the concept that we're looking at. So this first one on the linked list, you're going to write a program that can be used for a database of students. And it goes through like a problem scenario. I'm not going to read through it right now, but you'll notice at the bottom, it says implement the above program in any programming language, using any technique that you want to meet the requirements as described above. But the described above is talking about a linked list. So as an example, if you're writing this in C++, you'd actually have to create your own data structure called a linked list, and we'll talk about linked lists in the course. That's probably the first structure we'll talk about. And then you'll end up having to do a lot more work actually. And if you did it in Java, like the book's going to show you the package that you import in the library, you basically create a new object, call it a linked list. And I'll have some examples, and I'll show you how to do that. In fact, I did that. I will be doing that as well in the Java course, so you have a little overlap there. But able to use any technique, which means you can make this course as hard or as easy as you'd like. To make it a challenge, you use C or C++. To make it easy, you use Java, essentially. If you get the book will help you in terms of the implementation of all of these structures. So it cuts out about 90% of your Googling. Problem is when you Google and you look up information on the internet about linked lists, way too overwhelming. It's not a subject matter where you can just go to the internet and find solutions to stuff and learn information about things. It's just too complicated. It's like if you learn the foundational stuff, you could just do it yourself. A lot easier than trying to find examples of stuff. So let me go back to the syllabus real quick. So what we're looking at then is the same kind of thing I just went over with the Java course. We've got the final exam, that's worth 25%, midterm 25%, CSLO 25%, but only 4, so it's only 20%, but instead of doing, what did we get I moved the midterm up to 30 to take 5 points away. So instead of 5 or 6 assignments, you only have 4, but it's not meant to be a programming course. It's meant to be a, how could you take a data structures course without creating any data structures? So you're creating 4 of the most popular ones: the linked list, the collection, queue, the stack. You're gonna basically put some of this stuff into practice so you can kind of understand how it is. The final exam will not have any programming on it. It'll be a multiple choice type of exam, and again, it's based heavily out of the textbook. So that's why I highly recommend getting the textbook. If you don't get the textbook, it's going to be kind of hard for you to actually do well, I think, on the exams. I don't know. It's going to be more challenging without the book. And the book's light reading. It's like each chapter is like 10 or 12 pages or something. It's extremely lightweight reading. But it's action-packed. It's full of information, useful information. So here's kind of, you guys know the drill and everything else. I can skip through academic integrity, stuff like that. And you guys already know the drill on the schedule, same as before. But I just want to introduce some of the topics that we're going to cover in the course. And because today I want to actually go through Lecture 1, talk about the course. It's a very small lecture. And kind of introduce some of the topics that we're going to be covering. Because a lot of students actually don't know what data structures are about. And you sign up for a credit, they have a misconception, I guess it is. Off perception of data structures. Some students think that data structures is math. Some of them think, it's like not related to programming. I don't know. So by the end of today, you'll know what you're studying, at least. And I highly recommend this class as a foundation for computer science, for software engineering, for computer engineering, even for electrical engineering. Actually, it makes a lot of sense. And this is a foundational kind of course that helps your understanding. It would not be fair to skip the concept of algorithms. Data structures and algorithms are 2 separate concepts, however. So what's a data structure? Well, a list is a data structure. It's something that you're going to program. You're going to create this structure that's going to hold data by definition. And a list usually has a couple characteristics associated with it as a structure. It could be an ordered list. It could be an unordered list. There's certain things we do with the list. Like, for example, we have to put something into the list. We have to take something out of the list. Move things around in the list. We could also sort the list, sequentially, alphabetically. So as a structure, we build functionality from a programming perspective to work with the structure, to change the content, manipulate the content, get the content. So that's the basic concept of all of these structures. So with a stack and a queue, well, a stack is sort of like an unordered list by position. And a queue is, again, another concept that we're looking at, that it's going to also store items in sort of a list. So some of these structures work together by concept. When we're talking about the generic list, we're talking about the generic collection, talking about the generic, implementation of this particular structure, versus the concept of an algorithm. So An algorithm by nature, and I know this sounds kind of basic, but if you don't understand the concept of what you're looking at in this course, it's going to be hard to put it in perspective. Algorithms are more like routines or processes. They're sort of like a method. So an algorithm might be a search or a sort. So you would find some way, for example, a binary search is an algorithm. And a binary search takes a list of items, let's say, and cuts it in half and says, you know, is this item we're looking for in this search, because we're trying to find something in the list, is it above or below this point that we've identified? And we cut it in half again, and we cut it in half again, and you don't have to worry about not knowing what a binary search is at this point. But in comparison, the algorithm works with that data structure. The data structure is the list. So we have to actually kind of look at algorithms with data structures, but the focus of the course is on the structure. You could take an algorithm course. Usually, as an undergraduate student in computer science, you take data structures and you take algorithms, and it's usually called analysis of algorithms, because there's things that are inherent in algorithms that I'm going to talk about in lecture number 2 next week that are basic concepts. One of them in particular is the concept of efficiency. You know, there's many different ways of building the system or the method, the process of searching. You know, you could go one item, second item, third item, fourth item. And that's going to be slower than, binary search is actually a pretty effective method because it's quick. And so there's things in terms of the efficiency of the algorithm, the time it takes for the algorithm to complete by implementation. Do you want to hit that door? Is that what you're doing? Yeah, excellent idea. There's things that can be used. There's a thing on the bottom of the door. There you go. To describe the characteristics of algorithms. So in terms of our exposure to data structures, I'm also going to introduce the concept of algorithms in terms of what they're accomplishing. Because when we create the data structures, especially with the assignments, and we create a list, well, you have to actually implement an algorithm that's going to, let's say, for example, find an item in the list, you know, or search for an item, or pull something out. It's all algorithm-based that works with those data structures. And we can't implement any of this without any language foundation. So, were you in our C++ or were you in the Java course?
I took in this spring, Java.
Okay, good, good. Before you came in, I was telling, because some of these people, in fact, most of the class is actually taking the Java class concurrently. And as what I missed, and for anyone else that just came in, I don't know who came in after I said this, because some people came in later, that I'm going to base this off of Java. And that there's a book going around that's listed in the syllabus that you want to get. So in differences between this class and some other classes I've taught, this one, the book is required. It shouldn't be an expensive book, however, but it's the nature of the course just requires it. So it's a lot more specific than, like I say, a survey or an overview kind of course. It's not like there's a lot of literature on the topics either. It's more, you know, here's the technique. It's almost like a math class without a math book. It's hard to teach a math class without a math book. You have to have problems, you have to have exercises, you know, have explanations of how something is done. Could you take the leg out of the door, maybe? Just push it up. It should stand up on its own. And then just shut the door. Perfect. Thank you. No, just shut it. Yeah. Hopefully it won't lock. Incidentally, next week we'll be in the room next door. I don't like this room for many reasons. Why it gets warm actually in here. The next room, 102, gets hot. It gets cold. This room gets hot. This room has an echo. That room doesn't. And I like the door and the whole ambiance of that room better. Because I like to stand over there instead of over here. So it's just, I like that room better. So we're going in 102 next week for Monday and for Wednesday. But there's no Monday class because it's a holiday. So. All right, let's go back to the syllabus. So what do we got? So today I'm going to talk about the introduction, what you're studying in this course, go over the syllabus, stuff like that. Next week we're going to hit lecture 2, which is in the week 1 topic, but with such a low turnout today, and everybody thinks I don't start class the first week because traditionally I don't. So kind of odd. I just decided to do it anyway. So next week we'll cover again a little bit of the orientation of the course again, unfortunately, for the new people who just showed up. And then we'll also hit the lecture too. So today will be an easy course, or fast course. I'm also, after I talk about the concept overview, we're going to start out with collections as a concept. And if you were in my Java course, you already know how easy it is to create a collection. We're going to see a little bit more in terms of the implementation of that. If you don't know, if you're taking the Java course right now, don't worry about it. I'll go through it all, and it'll help you in the Java course. Then we're going to go right directly into link structures, and that first assignment is on a linked list. So we'll look at linked structures. And then we'll go into queues, lists. Queues, stacks, I just should actually say stacks on it. Queues and stacks are pretty easy. They're the same base concept, but they're used differently. And it's the algorithms, going back to the concept, that are changing the usage of the data structure in a lot of different ways. Are we inserting at the beginning of the list? Are we inserting at the end? Are we removing from the beginning? Or removing from the end? Which kind of changes this nature. We will look at recursion and the concept of it. Is it a data structure? Not exactly, but it works with data structures. And then also the concept of sorting and searching. Again, is it a data structure? Sort of an algorithm structure. So what I'm doing with this course is kind of making trees. Trees is a data structure. Definitely a data structure. So what I'm doing is I'm kind of mixing in some algorithm stuff. We don't actually have a analysis of algorithms course here. So this is kind of like data structures and algorithms, but primarily data structures, primarily mixed together. So we have assignment number 5. I think I only have 4 assignments. That's a typo. Looks like I have to fix this. Yeah, I only have 4 assignments. So I'll fix that. I have 5 assignments in the schedule and only 4 assignments in the syllabus. We only have 4 assignments, not to worry. And you can preview everything, as I mentioned before. It's out here and available for you to preview 1, 2, 3, 4. So, I don't have the CSL, I don't have the midterm yet, but you don't really need it yet. And just like this class works just like any other course you may have taken with me. Everything is due at the end of the course. Questions about the syllabus, the materials, the course, the book. The book's interesting. It's in the 3rd edition. The 3rd edition's been out for a year, which is good for you because you can buy a used edition of it. It's not like a brand new one. It's a 2010, and we're almost getting into 2012 soon. Another couple months. By the time this class is over with, we'll be in 2012. The book is almost 2 years old. It's a year and a half old, which is great because you can get it cheap. You can get it online. You can order it. You don't need it immediately. You can order it and get it like in a couple weeks. And it's really good reading. It's a fairly easy read book. So, I guess you could possibly share a copy amongst yourselves if you wanted to. That might also be a good solution. So, questions, comments, concerns about the syllabus, about the course? You guys are an easy group. Next week it'll be what? What do you mean? I don't understand. See, hear the echo? Go. It really comes out poorly on the video quality. All right, and who's got the book, actually? I need that book back. Oh, no? Okay, yeah. So if you came in late, there's a copy of the book going around. You can check it out, preview it, see if you want to order it. And these slides actually come from the book. So it kind of gives you a feel for what's in the book. But the slides are, maybe 18 slides for a chapter that's only about 20 pages. So the chapters are pretty short as well. It's great, great kind of easy read, easy to understand kind of book. So what I'm going to do is go over chapter number 1 in terms of the introduction to data structures. And unlike an undergraduate course, I'm going to assume that you've got some exposure to programming in any language. Doesn't really matter what language. Doesn't have to be Java. And I'm also going to assume you understand the concept of what an algorithm is, and hopefully you understand the concept of what a data structure is in terms of what it is we're doing it. So today I'm going to basically go over chapter 1, which is going into the concept of why do we want to use algorithms and why do we want to use data structures, but primarily focusing on the data structure concept. Next week with Chapter 2, I'm going to look at the analysis of the algorithms a bit. And then next week's going to be all about algorithm and introduction to kind of the efficiency component of it and how they work with data structures. And then we're going to move into collections. And we're going to go through it, data structure after data structure. So today is kind of like the overview of the design and the reasons why we're doing this. So identifying various different aspects of software quality. We're all familiar with the concept of spaghetti code, perhaps. Have you ever heard of the term spaghetti code? You serve it with a little bolognese sauce. Eat it with chopsticks or fork and spoon. No? Spaghetti. We know spaghetti. It's an American dish. And they used to call it spaghetti code. And then people say, well, why do I want spaghetti code's bad. You don't want to write spaghetti code. Spaghetti code has no structure to it, and it doesn't use data structures. So in the old days, people used to write spaghetti code. Hard to read. It wasn't that it wasn't documented. It wasn't that it wasn't using constructs. It just wasn't organized. So data structures help us organize the source code, and it leads to good software development. This course is not necessarily a software engineer. It is a good foundational course for software engineering, but we're not going to talk about software engineering. Instead, we're going to talk about how do we make the code efficient? How do we make the algorithms efficient? How do we put the data structures in there so we don't have spaghetti code, and nobody calls our code spaghetti code, because that's a bad connotation. It means, it's like trying to find a noodle in there. You can't. It's all mixed up with stuff. And sometimes people put and I'm going to have spaghetti tonight, I think. Now I'm hungry. Bell peppers and mushrooms, and you can put a bunch of stuff in there, mix it all up. And who knows what you're going to get with each fork bite. Hopefully we all had lunch, otherwise I'm making myself hungry. So data structures, put all the bell peppers on one side. It's kind of like those finicky eaters, get the plate and everything's separated. You take everything, put it over here, all the mushrooms over here, flat all the onions if you're me. Take all the spaghetti pieces, the pasta, put it all in one pile over here, organize everything. Keep it all separated so we know what we have, so we can use it. So each bite might have one piece of pasta, one piece of bell pepper, and one piece of mushroom on it. So when we eat it, it's balanced kind of thing, rather than just getting all sauce in one bite. So is really what data structures are doing for your source code in programming. It's the same concept. Because you could have 15 million variables all representing student names. And then you have 15 other, 20 other different variables all representing student GPAs. Or you can put it all together per student. So you have student name, student GPA, student grade. All the information about each student is all in one pile. All the information about this student is all in one pile. It's organized. So you want to know about student X, you just go to X and say, what all the information associated with you. Well, that's a data structure that you're creating that's encompassing data about a particular element or particular item, and you can organize it. Put it in a list, put it in a queue, put it in some kind of collection, and keep track of everything. So it takes away the spaghetti concept. So it's a way putting data structures in your code is a good thing to do because it eliminates the spaghetti code. So the motivation you need for data structures is based upon the quality issues. Higher quality software is structured. It's better structured. It's not spaghetti. Introduction to the basic concept of the data structure itself, purpose of this lecture, and also looking at elementary data structures in terms of what they are. So software engineering in general is supposed to be the study of techniques, theory, support for development of high-quality software data structures. This is support for structuring the software, which is what? Software is source code, documentation, anything that goes along with it, manuals and stuff. So data structures focuses on the software source code only. You can't apply data structures to documentation, to development cycles, to anything. So it's very specific in terms of how it's applied. Focuses on controlling the development process to achieve some sort of good results, having consistent structures used for the application, They're all using the same kinds of structures, hopefully. The best structure was selected. Why would you want to do a collection when you really want a list? Efficiency. So we want to satisfy the client, meet the needs of the user, make it run fast, make it work for its intended purpose, hopefully. A few things to keep in mind. So the goals of software engineering is usually to solve the right problem. So we're going to assume that we know everything else there is about software engineering. Now we're just focusing on the structure of that source code. We can actually facilitate better implementation of those requirements by designing the data structures along with the objects or the entities that we've identified. As an example, if we're doing like a student registration program, we can do a data structure to keep track of students, a data structure that keeps track of classes and of faculty, and put it all together in terms of the working system of the end product. It doesn't have to be the same data structure. It might actually be a different one for each one of the different things. We might have one main structure like a tree, as an example. It keeps track of all the smaller structures, so we might nest the structures. But what we're really looking at in terms of this class is not only what are the structures, but how do we put them together and how do we use them to come up with a good solution to the problem in terms of the software engineering problem solving. So more difficult than it might seem. Client interaction is key, finding out from the client. And, this is kind of all these software engineering books and concepts, chapter 1 always has an overlap between basic software engineering concepts. So I'm going to kind of skip through some of the stuff that you guys already know. Delivering a solution on time, under budget, yeah, right. So there's always some trade-offs. Delivery of the high-quality solution, beauty is in the eye of the beholder. Some people like spaghetti code. Don't know of anyone who really would admit that in public, though. They like to write spaghetti code. They might like to eat spaghetti, but they might not like to write spaghetti code. So I must consider the need of the stakeholders. So here, if you've never heard of the concept of aspects of good solid software engineering or software quality aspects, here's your little list. So I'm going to kind of skip through this. If you read chapter 1, you'll get the example. So let's go through a little bit of an example to kind of figure out. And what the interesting thing is, this is a nice example for what the programming assignments are going to do. So every one of the assignments has got a scenario. This particular one, let's take a look at this example as a kind of a means. And you have 4 of these that you're going to do. So you're going to give it a problem scenario. Here's some data. They're all associated with tracking data. Here's some data that we need to track, customers. And here's some data that we need to track. And it's a very data-centric kind of problem-solving approach. So consider the problem of storing containers being unloaded at a dock. We're going to write a program, a programming language, to keep track of these containers that are being unloaded at a dock. Kind of boring, but containers could immediately be loaded onto waiting trains and trucks. We have a shipping dock. Saying there are some trucks that are going to come up. We're going to load the containers on these trucks. Efficient for the dock workers, but not very efficient for the railroad and the trucking companies. But maybe for the dock workers, unloading stuff on a dock, container might be efficient, kind of as a problem. So what do we know about each one of the containers from a data analysis perspective? We know the size and the shape of the containers. And we know that each one of them has a unique ID because it's associated with some sort of destination, as an example. And we have dock workers that need to know what is in each one of the containers. Is it perishable? Does it need to be refrigerated or something? So we have the information that we have about each one of the data components that we're looking to store. And the containers, they could simply be offloaded and stored on the dock as they are unloaded. So it's kind of like you've got your plate of spaghetti, going back to the spaghetti concept, and the spaghetti's full of stuff. There's a meat sauce with mushrooms and bell peppers and stuff in it. Sounds like a pretty good plate of spaghetti. If you're going to figure out, well, we're going to unload this spaghetti plate onto a table or onto other platters, how are we going to do it? Which is essentially equivalent to this docking thing. We got a container full of stuff, and we're going to need to unload this stuff onto a dock. And some of the stuff is going on trucks, and some of it's going on another boat, or some of it's going on trains. You know, it's going to different places. So we could organize it, let's say, by its ID. We can put it into groups, let's say. We can spread it all out by its destination. We could just unload it all. Don't care about the order. Just put it all on the dock, and you take it from the dock and sort it out per destination. So we've got choices. There's usually more than one way of doing it, actually. So if the containers are simply just offloaded, stored on the dock as they're unloaded, in the order in which they're taken off the truck, has anyone actually ever experienced the concept of moving? This is a very equivalent. Actually, if we could write data structures to organize a move, that would be efficient. People do that, actually. They've got, for example, you're moving your apartment, you're moving from one city to another, and you rent a U-Haul truck, or a truck, right? You got to fill the truck up with all your personal belongings, and then when you get to your destination, you got to unload the truck and put everything away. There are some people that just open up the truck. I've seen this happen, actually. I've helped people, too many people I've helped moved. They open up the back of the U-Haul truck, and you just start putting stuff in. Couches and chairs, and nothing is organized. You have a couple of the loads have all the furniture in it, a couple of the loads have miscellaneous stuff. So the smart mover takes and packs stuff up correctly. All the dishes go into one box, and then they're marked dishes. All of the pictures and frames are all put in, bubble wrap and stuff, and they're all marked in boxes called pictures. And each one of the rooms, you can do it by room, bedroom, bathroom, are all marked. So when you get to the new home, you take the bathroom box and you stick it in the bathroom. Kitchen boxes go into the kitchen, and then you can unload it. This is exactly what you're doing with software engineering and with data structures. You're taking the information, the data that you're storing in your application, and you're putting in a kitchen box, in a bathroom box, and in a refrigerator box. And those boxes are your data structures. It's going to be a collection. In this particular case, I'd probably use a collection. Does it really matter the order of the dishes and plates and stuff? No. But you're storing all those items in the structure, aka the box, and you're using them to make your job more efficient. And your job is eventually you're going to have to unload all this stuff. So you're in the kitchen, or you're going to have to go, where's the kitchen? Oh, they're in the bathroom. You got to go to the bathroom and grab the kitchen boxes. So same goal as what you're accomplishing in software engineering. You're going to pack it up, you're going to unpack it, you're going to make it efficient, make it useful. So going back to this example here, if we just unloaded the truck and stuck it all on the dock, unload the U-Haul truck and just stick it all in the living room, which a lot of people do for some reason. You got boxes in the living room. It takes you longer to unload everything. Well, it's actually quick out of the box. Quick out of the truck. It takes you longer to find the boxes. I love those people that load everything in the garage. And then the stuff just sits there for years. And then you go, well, didn't we have plates? Oh, just buy new ones. Don't we have furniture? Ah, it's in the garage. And they just end up buying new stuff and then the stuff in the garage. And eventually they have a garage sale. They get rid of all that stuff they never unloaded. So it's efficient for unloading. It's quick to get that truck unloaded. But it's not efficient for finding and loading the storage containers onto the truck and the trains, in this particular example, instead of putting the furniture in the right rooms. This container, this box has to go on a truck. This one has to go on a train. Not very efficient for that purpose. And it requires a linear search of the entire storage area. Each time a container needs to be found. It's like when you walk out to the garage and you got to look at every single box to find the one that goes in the bathroom. Because you need toilet paper. It's in a box. It's in the garage. We unloaded it. So it's a linear search. So this is how those data structures work with algorithms. If you create the data structure to put everything in a huge collection, you got to linear search it, which is a slower algorithm to go find the box of toilet paper. That's why people just go to the store and they buy more, and they leave the garage alone. It takes too long to go through the find stuff. So that's the relationship between that data structure and the algorithms. The data structures are going to determine which algorithm options you have available. Can you do a binary search in the garage? Nope. It's not ordered. There's no order to it. It's chaos. You got to go through. It lends itself to a linear search, just like this container problem does. So what if you lay out every large array? So what if we lay out a very large array so that each storage container is indexed by its ID? We get smart. And we go, okay, we're going to pack everything up. We're going to put numbers on the boxes. Well, we all know about arrays, and the problem with arrays in programming languages is it's hard to insert. So here's what happens with the boxes. Put number 1, kitchen, number 2, kitchen, number 3, kitchen. And then you start number 4 is the bathroom. Oh, another kitchen box. Uh-oh. So you take the 4 on the bathroom and you cross it out and you put kitchen. Oh, number 4 is kitchen. And then you start changing numbers around, and then the organization turns into spaghetti code. Because you've made something that was structured unstructured by the problem of having to be able to insert something with unique IDs, which is the problem of arrays. So an array is a primitive data structure. It's a start. You know, it's not a bad, and it could also be considered it's a structure. Is it a real data structure? It's a programming language construct that's used as a data structure in theory. Not very efficient. So the ID is unique for all of the storage containers. Array would be very large. You'd have one numbering system for everything. That's such a good thing. Array would be mostly be empty, possibly. We might not fill up all the spots. Significant waste of space might exist. Especially if you had to, in a programming world, you have to determine the size of the array, usually ahead of time in most modern day languages. So if you wanted to create an array for how many boxes you might have in your house, thousands? I don't know, hundreds? You got to pick a number out of thin air and go, I'm going to make the array this big. And your numbering system is limited by your array. So what if you use the same solution but allow the list to expand and contract to eliminate some of the empty slots? And then we're looking at a linked structure, which is one of the first structures we're going to look at in this course, which is a more sophisticated data structure that we're going to put together to store these containers, to store these items or these boxes or whatever it is we're wanting to store. And what we're storing is data. We're storing data about the contents of the box that we've unloaded from the truck, the contents, the order, its destination, all the information that we need to keep track of it. We put in a more elaborate, sophisticated data structure, which is why you take a data structure course. Because then you know what all these structures are, and then it opens the door to, let's use this, let's use a queue for this, let's use a stack for that kind of thing. And then we can kind of relate it to problem solutions. So the array would always be ordered by ID. Find a container would be easier if we used a more elaborate expansion on the concept of the list. And however, we'd face containers to be moved multiple times as each new container are added or removed. So lists also have that option of having to move things over. So we have different list options, however. So we can create a list that might actually be more effective than another one. So we consider what we know about each one of the containers. Problem mistake a lot of people do is they like trying to make the data identify itself, which is something that is also inefficient. You can see this real easily by looking at spaghetti code. Going back to that concept, when people don't use data structures, so they got 20 variables that are representing 20 boxes, and it's box 1, box 2, box 3, box 4. And then they move the boxes around because they got to change the order, so they change the numbering, and then they mess the numbering up. Something ends up getting deleted incorrectly or moved around incorrectly. And then it gets very hard to follow it. You have more operation, more computation going on. So one of the goals of the effective data structure is not making the data self-identifiable, making the structure work on any of the items. So we have an independent identity of the items. So we have a list of boxes. all boxes are the same. It doesn't matter which box we're looking at. Because the first mistake people try to do is they go, well, we have kitchen boxes, we have bathroom boxes, we have, and then they're all different boxes. You got 20 million data structures set up for the different list items of different types of boxes. But a box is a box. So we make it kind of generic. Don't make the item self-identifiable, but make the structure work so we can manipulate the list outside of the contents, outside of what we're actually keeping track of for the data. So that's probably one of the most interesting concepts in terms of determining how to design the data structure. It's keeping in mind what the structure is actually trying to accomplish. So considering what we know about each one of the containers, the ID number should give us the destination of each container, perhaps, making the structure more elaborate to say all of the 200 level items are truck items, all of the 300 level items. All the items are the same. They're all items, but maybe one branch of the item goes to the trucks and one branch goes to the ships or something, or to the buses. So then we can create an array of the destinations where each cell in the array is an array of containers. Maybe not that kind of efficient, maybe not the best solution, but it's a start. Anything past using single variables is a good start. So now we can store the containers for each one of the destinations in a variety of different ways. And here's some options. And this is what we're looking at in terms of the solution to this problem using data structures. We can store it in the order they are unloaded, for example, with the first one unloaded being the first one shipped in a queue. Actually, it's kind of interesting. I've never actually looked into package handling, but I think it might be interesting to see what kind of data structures they use for that. Because it's quick. They know exactly what happened to that package. You can track packages easily. And there's a global numbering system, but then there's also like things that go airmail are tracked differently than things that go ground. These are overnight service, different qualities of service, have different tracking. And you know, just because you have a whole big old bucket of stuff, big old container of stuff that gets loaded in a truck, how are you going to put, is it going to be first come, first serve? In a queue kind of thing, first in, first out? Or maybe, if you did that, if you were unloading a big old FedEx truck and you had an hour before the plane left, it's actually kind of like when you go to the airport and you're waiting in a check-in line and everyone's got different flights. Your flight's leaving in 5 minutes. Usually you see those people that are like freaking out, and sometimes they go, hey, my flight's going to leave. Do I have to wait for these 20 people in line ahead of me? Which would make a queue really ugly. It's like, no. Forget the queue structure. Pull you out, put you in a different queue. So I'll help you right now so you can get on your flight. Because there's people that miss flights, actually. In the old days, they never used to let you get out of that line. You'd miss flights or they hold the plane. We have confirmed passengers that are still over there in baggage checking. But it depends on what the goal is in terms of the solution to the problem. But a queue creates issues for those packages. Just because it's the first item off the truck, it's going UPS ground. What about the ones that are going airmail that need to leave in 5 minutes? They're going to be lost in the back of that queue. You can store it in the order that they are unloaded, with the last one unloaded being in the first one shipped. And that would be a stack kind of concept, changing the order. Or you could store maybe by ID with the destination in an ordered list. Makes a little bit more sense for this problem solution, actually, because now we can take, you're all airmail, get you over here, ground, get you over here, and then you can have separate queues. And you can have them ordered in terms of when you arrived, cutoffs. In particular, shipping application, I don't know if you'd actually do it in any type of an order. You'd do it, this is a batch, we have to process the batch. And when the batch is done, then the plane leaves, kind of thing, or something. So, but these are sort of the topics in the introduction to the concept of data structures that we're looking at in this course, and this is pretty much chapter number 1 of that book, which gives you that kind of the overview of some of the decision making that goes on when developing the source code content. So it's not necessarily the application development that we're looking at in this course. We're not looking at the methodology. These concepts would apply if we were writing it in a procedural, object-oriented, functional language. It doesn't really matter what kind of language you're implementing this in. It's the overall data structure concept. How are you going to structure the data? And it's usually based on what are you going to do with the data? What do you need the data for? And then your structure is going to determine how efficient your algorithms are. So next week's topic actually looks at the concept of algorithms and an introduction to algorithm efficiency, which is chapter 2. I want to save it for next week actually because we're going to get brand new people that are going to come in thinking the class starts next week. So, but it's kind of that was a kind of a run through on chapter 1 of the book, and a run through on the introduction of the course, and a run through on all of the first day logistics. Are there, and as I mentioned earlier, the book is required. You can get by without buying it if you want to share a copy. Hopefully you guys had an opportunity to look at it. But you at least have to get a copy to share or something. It's because, in the lecture material, I can't cover every detail in terms of every one of those structures. I'll be boring you to death. It's better to actually read it and implement it on your own. Questions, comments, concerns? Everybody know what the class is about now, at least? I actually did get a couple of emails, kind of odd ones. No, it's not math. It doesn't count. This class does not count as a math requirement. I'm sorry. It's not a math class. I don't know why somebody would think that data structures would be a math class. I don't know. They've never heard of the concept, perhaps. Well, if you're not coming from a programming language background, if you don't have an undergraduate degree in computer science or something, you would not know what data structures were, I think. Then we're done for today, if we don't have any questions or comments or anything. So go out, go shopping online, see if you can buy the book cheap. You can get a good price on that book. And then read chapters number 1 and number 2, and come back next week, and we'll go over the same thing. Well, hopefully not the same thing, although we're going to get a lot of new people. But we'll go over chapter number 2, move straight forward. Okay, we're done. Bye-bye.